Now let's look at the remainder of an alternating series. A remainder is how far off the approximation is from the actual answer. So the remainder from using the nth partial sum to approximate the infinite sum S, okay, I'm just looking at that absolute error. This is my nth partial sum that we're using to approximate S, which is actually the infinite sum. And so R sub n is the remainder by using that nth partial sum for an approximation. Now look at S sub n. Let's say that we've added the first n terms together, and now we're going to add the next one, which is going to be negative in this particular case. We're now going to be subtracting the n plus first term. Okay, let's look at this. A1 plus A2 plus so we're going to have plus a sub n minus a sub n plus 1, and we'll just continue here. This is the nth partial sum. And so now the n plus first partial sum will be what you get by just subtracting one more term. Now the amount of the term that we just subtracted, a sub n plus 1, is actually the distance from here to this term, the n plus first partial sum. So this distance right here is a sub n plus 1. Now, remember those terms, the alternating, every other term is coming down close to this infinite sum, and every other term is of the partial sums is actually increasing closer and closer to this infinite sum. Okay? This actual limit is somewhere in between the S sub n and the S sub n plus 1 terms. Each time, two consecutive terms have that infinite series sum trapped between them. So if I look at this n plus first term, which is this distance here, that term itself is actually larger than what the difference between S sub n plus 1. If I take the absolute value of that, well, that absolute value is just the absolute value of the a sub n plus 1. Okay? This is just that n plus first term. Okay? And so this remainder is going to always be, okay, it is just S minus S sub n, but I know that's less than or equal. The difference between the sum and the nth partial sum, so that would be between here and the nth partial sum, is actually smaller than what the difference is between the n plus first and the nth term, which would be from here to here. But that difference is just that one term. Okay, so what this remainder theorem is saying is that if we have an alternating series, then the remainder is less than or equal to that next term, the n plus first term. So the remainder for using S sub n as an approximation will be the size of this term right here. So that number itself will be greater than or equal to how far off the nth partial sum is from the exact infinite sum. Okay, so the remainder is less than or equal to the magnitude of the first neglected term, that n plus first term. Okay, so let's say we want to find out how many terms do we need to actually add in this series to approximate the values of this series. And I want the approximation to be less than 10 to the minus 6. Okay, so if I want to find how many terms, but I want the error to be less than 10 to the minus 6, that means I want R sub n to be less than 10 to the minus 6. R sub n is that remainder. So it's how much off we are from the real answer. Well, R sub n, we know it is also smaller than a sub n plus 1. So if we want R sub n to be less than 10 to the minus 6, we can just make sure a sub n plus 1 is less than 10 to the minus 6. Well, what is a sub n plus 1 in this particular series? Don't worry about the minus 1 to the k plus 1. That's just giving us the alternating feature. The a sub n plus 1 in this case is the 1 over n plus 1. So right here I see that a sub k is 1 over k. And so a sub n plus 1 will be 1 over n plus 1. I'm just replacing the k here with n plus 1. And that's less than 10 to the minus 6. So if I want 1 over n plus 1 to be less than 10 to the minus 6, let me rewrite this. That's 1 over n plus 1 less than 1 over 10 to the 6th. I can now take the reciprocal of both sides, which n plus 1 on the left, 10 to the 6th on the right, and you reverse the inequality when you take the reciprocal of both sides of an inequality. So that means that n plus 1 must be greater than 10 to the 6th. Okay? So if I'm trying to find n, I just need to choose n to be at least 10 to the 6th. Okay? So I just want the n to be bigger than 1,000,000 minus 1, so choose n equal to 1,000,000. Okay? So I need to have 1,000,000 terms for this infinite sum to actually have a value that's correct to 6 decimal places. It ends up that this actually converges to natural log of 2. So you'd have to add 1,000,000 terms of that series to get that much accuracy, 6 decimal places of accuracy for natural log of 2. So that's a bunch of terms. Okay, the next one. I want to find how many terms I'd need to add so that this series will be within 10 to the minus 6. Well, I know the remainder, which is just the a sub n plus first term, or it's less than or equal to the a sub n plus first term. If I want that remainder to be less than 10 to the minus 6, I can choose the n plus 1 so that a sub n plus 1 is less than 10 to the minus 6. Well, a sub n plus 1, this rule here tells me that the a sub k is equal to 1 over k factorial. So that means that a sub n plus 1 is 1 over n plus 1 factorial. So I've got 1 over n plus 1 factorial, and I want that less than, and I'm going to rewrite 10 to the minus 6 is 1 over 10 to the 6th, and now I'll take the reciprocal of both sides. N plus 1 factorial is greater than 10 to the 6th. Now this one's a little harder. You can't just add or subtract something to both sides. So what you need to do is look at your either a table of factorials or calculate some of the factorials. And you'll see that 9 factorial is actually 362,880, which is less than 1,000,000, which is 10 to the 6th. But 10 factorial, we're just going to multiply 10 now, is 3,628,800, which is now greater than 10 to the 6th. So if we want this inequality to be true, I know that n plus 1, for it to be greater than 10 to the 6th, n plus 1 must be 10, which means that n has to be 9. What that says is that if I take 9 terms here, which isn't very many, 9's doable, 1,000,000 isn't. Take 9 terms here, and we're going to be within 10 to the minus 6 of the correct answer for this infinite sum. Now this infinite sum actually converges to e to the minus 1 minus 1. So if you actually calculate this on your calculator, you're going to have as much accuracy as what your calculator will show. And it'll take you 9 terms of this infinite series to get within, 10 to the minus 6 of that actual answer. Okay? And calculators have, I'm not sure if that's what they're using now, but to evaluate exponential functions, trig functions, they actually can use these infinite sums to actually get the accuracy that you need, for your display.